Okay, hey, today we're doing functional groups. Now, functional groups can be any number of things, but today we are talking about all of the attachments that you can put onto a carbon chain. And we have a bunch of those listed for us on table R, which comes right in here. So you should remember that table P is going to give us the number of prefixes based on the number of carbons in our molecule. And then table Q is going to show us the basic formula for hydrocarbons, meaning with no attachments. So you can always use table P, but for table Q, that's just for hydrocarbons. And then table R is once we start adding new atoms that are not carbon and hydrogen. So there are a bunch of different functional groups here. I don't want to spend too much time dwelling on them because this video could very easily be hours long. I just want to get to the gist of it. I'm going to show you just a few, and that's it. So the first thing, where am I? The first thing that I want to do is draw you a halogen. Nope, strike that. I'm not going to draw it. We are going to look right here. So very first functional group here is called a halocarbon, meaning that there is a halogen somewhere on our hydrocarbon, which makes it a halocarbon instead of a hydrocarbon. So we can add any of the halogens, a fluorine, a chlorine, a bromine, or an iodine. This general formula is basically showing us what our molecule looks like, and we're just going to imagine that R stands for the rest of the carbon chain. So right here we have our example of a halocarbon. It is given to us as 2-chloropropane, and this specific formula is called a condensed formula. I want to show you the structural formula, which is actually the drawing. So here we go. We are going to look at 2-chloropropane. You should remember that propanes have 3 carbons, all single bonds. So I'm going to draw that. Voila. Now I need to take a chlorine and I need to put it on carbon 2. Because there's only 3 carbons here, any which way I number this, carbon 2 is going to be the one in the middle. You can put this chlorine on the top or on the bottom. I'm just going to put it on the bottom for the sake of space. And now I just need to fill in hydrogens to show that this guy is actually bonded. So you should remember that carbons bond 4 times, so each carbon needs to have 4 bonds. And you should remember all the way back from bonding that chlorine just likes to bond once. So chlorine does not get any hydrogens attached to it. It just bonds once to the carbon, and that is it. So that is what 2-chloropropane would look like. Now, you can add multiple halogens to your molecules. So we could do something like this where we have, let's do this. That base would be a propane because we have 3 carbons with all single bonds. And then let's pop, for fun, let's put a chlorine right here, and we will put a bromine beside it. Voila. So in this case, I would have 2 dangles, which means I need, oh, geez Louise. I have 2 dangles, so I need 2 numbers. I need 2 prefixes showing me what is on my propane. So I'm going to number this in both directions. I'm going to number it 1, 2, 3, and then I'm going to pick a different color and I'm going to number it backwards. 1, 2, 3. Now, excuse me, my chlorine can either be on carbon 1 or on carbon 3, and my bromine either way is going to wind up on carbon 2. So if I am going to follow the rules, I would want my chlorine to be on carbon 1 and bromine on 2 because that is going to give me the smallest sum of numbers. So I'm going to put a 2 bromo, and a 1 chloro. Now, when it comes to the name, I want my things to be in alphabetical order, even if that messes up the order of the numbers. So that means in my formal name, bromine is going to come first. So this is 2 and a bromo. We're going to put a comma. I'm going to put a 1. We have to put a comma because otherwise it may look like 21, and we don't want it to look like that. So we have 2, 1, bromo, chloro, propane. And just like before, the first number applies to the first dangle, and the second number applies to the second dangle. So that is what this could look like. If I had 2 chlorines here, I would need 2 numbers, and then I would say it's dichloro for 2 chlorines, even if that number, even if they show up on the same carbon. For instance, if I had something like this, and I had a chlorine, I had a chlorine here, and I had a chlorine here, and then we filled this up with hydrogen so that it was correct. Remember, each carbon bonds 4 times. I'm going to look for my base. My base is a 3 carbon chain. All of those carbons are single bonded, so this would be a propane. And then I have a chlorine here and a chlorine here. They are both on carbon 1, so this would be 1, 1, dichloropropane. Just like this. So that's really as extensive as it gets with the halogens. And that's that. If you can do this, you can just about do anything with those halogens. The next thing I want to talk about is alcohols. Alcohols are molecules that have an OH somewhere on them. And what an alcohol does to the name is, let's say I had, for instance, this right here, 1-propanol. I'm going to draw that. Let me copy the name here. And then we can kind of dissect it together. So this is telling me that I have, come back. I have a 3-carbon single bonded chain. What happens is this OL means that I have an alcohol. Oh, where'd it go? Can we get rid of this pages? Thank you. This OL here is telling me that I have an alcohol. For some of these things, they're where they fit in the name is different. So for the chlorines and the other halogen atoms, you can see that they go in the beginning. For the alcohol, it goes at the end. And this is why we love table R, because it's going to show us an example of what actually we're looking at. So this is actually saying that I have an OH on the first carbon of a 3-carbon single bonded chain. So the prop is telling me I have 3 carbons. The an is short for ane. It's telling me that all these carbons have single bonds. And then on my first carbon, I have an alcohol group or an OH group. And then I would fill up the rest of this with hydrogens. And that is what my molecule would look like. And that's it. This is an alcohol. No, not all alcohols are drinking alcohols. Only ethanol is a drinking alcohol. The rest of them are just called alcohols. So that's what we have. That is propanol. Now this OH can go on the end, or it can go anywhere in the middle of the carbon chain. It's just that it has to have a number. Now, in ether, you may have heard this. They've used this term a few times in science and in like fantasy writing, the ether and whatever. What it actually is is an oxygen that jumps inside the middle of a carbon chain. And then we would name the ends of that carbon chain as if they were dangles. So methyl ethyl ether means that on one side of my oxygen, I have one carbon, and then on the other side, I have two carbons. And we just assume that those are saturated all the way. This technically is an error in the New York State reference table. They wrote this in 2011 and they have not edited it. These are supposed to be in alphabetical order. So technically the name of this is actually ethyl methyl ether. Still supposed to be in alphabetical order, but you would name both sides as if they were dangles. So if you had 5 carbons on one side, that would be a pentyl. If you had 4 carbons on the other side, it would be a butyl, etc., etc. Okay, next one is an aldehyde. An aldehyde has a double bonded oxygen, and this those 2 lines you should remember are double bonds. Oxygen is going to bond twice, so it's only going to bond to that carbon because it's bonding 2 times to the carbon. And an aldehyde is special because this double bonded O has to be on carbon 1. That's what makes it special. If you remember hydrogen bonding is hydrogen plus fluorine, oxygen, or nitrogen. Aldehydes are special because this oxygen is on the end, and because it's on the end, it makes it much easier for atoms to find that oxygen and have intermolecular forces with that oxygen. So because of that hydrogen bonding aspect and that oxygen being on the end, it got a special name. So technically, these guys don't need a number because it will always be on carbon 1. If you put a 1, no one would mark it wrong, but technically you don't need one because all aldehydes are on carbon 1. Now, this would be pronounced propanal or propanol. It's very different from propanol because this has an OH and that O is single bonded, where here we have propanal with a double bonded O and the H is separate. So spelling does count for organic, unfortunately. It makes a huge difference. This is why we love table R, because it's super helpful. Ketones are things where that double bonded O is somewhere in the middle of the chain. So 2-pentanone, this tells me that I have 5 carbons. Those carbons are single bonded to each other, and the ONE ending is stolen from ketone, and it tells me that my double bonded oxygen is on the second carbon. So if you were to count it here, we have 1, 2, 3, 4, 5 carbons. That's why this double bonded O looks like it's attached to carbon 2. It's because it is. Okay, next we have organic acids, and this is where we had a teeny tiny bit of issues with the acid-base unit. It's because the organic acid has the COOH group. It means that somewhere, on the end of the molecule, we have a double bonded oxygen and we have an OH group. It's kind of like a combination of a ketone and an alcohol together, just smushed, or actually better, an aldehyde and an alcohol together because it needs to be on carbon 1. That's why this baby doesn't have any number here. It's because it's always going to show up on the end. This actually does make an acid. According to the Arrhenius theory, this is the H that would pop off as H plus when it is dissolved. But because of this COOH nonsense, this OH makes people think that organic acids are bases because they think that the OH is what dissociates off, but it's not the OH, it's just the H. Okay, just 3 more. We also have esters, and esters are a huge pain in the tush to name, so I'm going to go over it. Esters have a double bonded oxygen as well as an interrupting oxygen. So this that I have drawn, let me show you in a second. It is methyl propanoate. Okay. This baby is methylpropanoate, and this is what is in the reference tables as our example. So this is an ester. And the way that esters are named is that you would split this molecule at the interrupting oxygen. Okay? And the side that has the double bonded oxygen is considered the main chain. That's why propan is our base here. That is because we have 1, 2, 3 carbons and they're all single bonded. Then this baby over here is considered the dangle because it does not have an oxygen with it. And that's why we have methylpropanoate. Okay, so when we name esters, they're going to have a double bonded oxygen and an interrupting oxygen. Here's our double bonded, and here is our interrupter. He's interrupting the carbon chain. We split the carbon chain on that interrupting oxygen because we don't like when things are interrupted. It's rude. So we split it right there. We karate chop that oxygen, and the part that has the double bonded oxygen is our base. Now, sometimes this base is smaller than the dangle. That happens. You could have a really tiny main chain and then a super huge dangle. That's okay, because when it comes to esters, whoever has the double bonded oxygen is the king. So this can get a little frustrating, but if you really know how to read table R, it's kind of not too bad, because we can see here that if this is our condensed formula, if we were to split the molecule here on that interrupting oxygen, the CH3, we know that that's a methyl group. That's one carbon with its 3 hydrogens that are going to satisfy all of its bonds. That is considered the dangle. And then the part that has the double bonded oxygen here, this is our main part with 1, 2, 3 carbons, and that's where the prop comes from. Okay. Last, we have amines and amides. Some people pronounce these amides, just in case you come across that at some point. Can I scroll to the side? There we have it. Okay, so amines are going to be nitrogens that are inside of the chain. So here we have a nitrogen on the end. That's why it's getting a prop. And the entire ending is amine. So we have prop for our 3 carbons. 1, 2, 3. This "and" right here is for the single bonds between those carbons. And then amine is telling us that we have a nitrogen in here. That nitrogen sometimes will be more than likely attached to hydrogens. You should remember from the bonding unit that nitrogen has 5 valence electrons, so it needs to bond 3 more times in order to get its full valence. So nitrogen is bonded to the carbon chain and then to 2 hydrogens, and that's how it's going to get its full valence. And then lastly, we have amides or amides, and those are nitrogens that are paired with a double bonded oxygen. So this nitrogen here is bonded to a carbon, it is bonded to a hydrogen, and then it can be bonded to more carbons. In this case, it's on the end. Usually for high school chemistry, you're going to find these guys on the end. And again, they are different from each other because of the intermolecular forces. When we have an oxygen and a nitrogen here, the IMFs are entirely different from when we don't have an oxygen. So they are given special names. And that's about it. You just stick the amide on the end. And that's the gist of it. If you can draw alkanes, alkenes, and alkynes, and you're pretty good at naming dangles, then the functional groups is really just the ability, sorry about the dog, really just the ability to decipher table R. And then there's just a few things that are a little weird that are standout. That is going to be the ether with the interrupting oxygen, The fact that the only difference between an aldehyde and a ketone is that the aldehyde is always on carbon 1 and the ketone is somewhere in the middle of the chain. And our organic acids technically are a 4-atom functional group. It's COOH. And this actually comes up quite a bit in acid-base, that it's not the OH that dissociates off, it's just the H. It comes off as H+. For our esters, we have a double-bonded oxygen and an interrupting oxygen. And we karate chop the interrupting oxygen because it is rude to interrupt. And then our double-bonded oxygen is considered the main chain. The double bond sticks to the main chain. And then that's it. The amines and the amides are pretty straightforward. So that's it. If you have any questions, leave a comment. I will do my best to get back to you. And that is all.